and welcome back. Now let's see a really nice example in which we try to compute pi. First we'll try it in serial and then we'll try it in parallel and see if we can do this. We like this problem because we call it embarrassingly parallel. It slices up really neatly into different slices of problems that can be farmed out to workers, and they come back and each of the workers doesn't need the neighbor's value. There's not a lot of communication between them. I'll just do my job and then give it back and then you kind of put it all together at the end. So it's a nice fork and join model. There are two ways to do this. This is the traditional way. If you were to look at x squared plus y squared equals 1, that's a circle of area 1. And if you looked at a quarter of that, so the top right corner, if you just solve that for y, you get y equals 1 minus x squared, square root of 1 minus x squared. That's the upper right value. That's the upper right value here. If I do this and look at this, this is an area 1. This is area pi, radius 1, and the area equals pi. This is simply y equals square root of 1 minus x squared. And if I integrate this from 0 to pi, I'm going to get a quarter because I'm going to get a quarter of pi. 0 to 1, I'm going to get a quarter pi. If I multiply that by 4, I get pi. So this is just integrating this equation just from here, just this curve. And I say, what's this area in here? And this is 1. And I integrate this, and this is height 1 also. This is square root of 1 minus x squared. But I multiply that by 4. And I integrate between 0 and 1, I get pi. So this is mathematical tell me I have just pi. This doesn't tie today, it's just that it says pi is a number, and there. There's another analogy, which this curve, this is beautiful. This is also, if you integrate this from 0 to 1, pi, which is a nice curve. It looks like that picture on the right, you see? What we like about this over the top one is that square root can be slow from a floating point calculation point of view, but squaring is really easy. So we can do multiplication really fast, much better than square root. So we're going to try this one, and we'll see if we can integrate this again from 0 to 1 and do this. So remember, it's 4 over 1 plus x squared. And here's a piece of code that does this serially. Here's what we're trying to get to at the top, 3.14159, 26535, 897932, 384, etc. So let's look at what this code does. I have only 10 steps, so only 10 different rectangles to approximate my area. And the step size is 1 over the number of steps. So that's the width of each of those rectangles. If I remember, look at this. What's the width of that rectangle? That's step. Okay, what's the height? Well, remember this before. The height is 4 over 1 plus x squared. And so this is 4 over 1 plus x squared. Wherever the value of x is a value from 0 to 1. So I initialize my accumulator sum as 0, and then I'm going to go through, you always want to iterate on integer values. You don't want to be iterating on floating point values. So I'm going to count how many steps, because you always have a very clean cut line. Floating point has this noise, right, rounding noise, so you don't want to have, well, sometimes I ended up having some number of iterations, sometimes some other number based on the noise. I want to have a clean number of iterations. Now I have exactly here num steps iterations. X is going to continue to move to the right. So here's the value, here's the value of x as it continues to move to the right. As I continue to move to the right here. Sum starts at 0, and is going to be the area of that rectangle. This is the width, and this is the height. Okay, so none of that's magic. And I'm doing that here. And when I'm all done, I print out the value of pi. Let's see what I get. Well, I'm trying to get 3.14159.26535. Well, I got to the 2. Well, it's supposed to be a 1. 3.141. I didn't even get there. So I got 2 significant figures. If I increase num steps, I do very well. I would, increase num steps to the biggest number I possibly can handle. I would do really well. Take a long time, but I do very well. Not very accurate. So let's increase the num steps and let's parallelize. Let's actually play with this and see how close we can get. Parallelization version. Boy, I wish there were a way. I wish certainly there were a way to just have a one-line change and make this work. We do. That pragma we talked about before, that pragma parallel for, and I'm now done. So I'm now going to parallelize that for loop. OpenMP does all the hard work. I obviously have to add the include file, but it's all I'm going to add. I love this. Isn't it nice? 2 lines I add, and this thing is now parallelized. Num steps is still 10, and we can see what happens. Here we go. Here's my parallel 4. I'm going to sum plus equals. Let's see what happens here. All right, it looks pretty good. And, uh-oh, I've got a problem. Why is there a problem? Let me see what the problem is here. each thread needs access to this shared element. The whole idea of parallelization, one of the core ideas of parallelizing anything, just in life, anything, is what are any shared resources? If I've got a shared resource, I really have to be very careful about the shared resource. If I have multiple workers all working on and reading and writing to a shared resource, imagine a Google Doc, and they're all reading and writing and copying and grabbing a thing and grabbing their own version, which is in their cache, and then putting it back. It could really be ugly. Google Doc is nice because it's not really their own copy of this, but if I had a folder and I'm copying a version of paper and I'm putting it back and then you're grabbing a copy, I'm writing in parallel, but there are issues like that. So this shared value sum is a problem. We don't like that. The code's gonna run sequentially. That sum, it knows that sum is sequentially. So we gotta think about how to do this in a way that I don't have this single sum that's gonna be shared across these guys. So let's do this. What if I do the same thing I did with my for loop and just slice it up and say sum 0, first thread, you're gonna deal with the left side of this, and you're gonna deal with the right side of this. And then I compute independently sum of 0 and sum of 1. So I'm gonna have this sum array that I independently compute and independently contribute to. So, here's just two accumulators. Rather than one accumulator, I'm gonna have multiple accumulators in parallel. And then, when I'm all done, I then add them up. The join is a sequential thing where I go through each of the sum. All right, what was yours? It's like all these workers went out and worked for me. How much you make? Okay, how much you make? How much you make? And I write them all down at the end of the day. But they all were doing their thing in parallel, working their job. At the end of the day, the boss asks you, how much did you make? And here it's saying, how much did you accumulate? How much area did you calculate? How much area did you calculate? Done. So that seems like the way we do this. So let's do a trial run here. So now, what do we change? Well, I'm going to hard code the number of threads to 4. We talked before about how to ask the total number of threads are, or I can set that somewhere. And by the way, here's the way I'm setting it. So num threads is this constant. I'm just setting it to 4. So I did that before. And I'm going to do my parallel loop. Here goes my sum, and I'm going to initialize my sum to 0. So it wasn't as easy as before. Before I had a one-liner, sum is 0. Now I have to write a little loop to initialize all my sum accumulators to be 0. I do the same thing. Everything's the same, except that what am I doing differently here? Here's this idea. Each of them is going to grab a different piece of that array, just like I was doing my for loop before. Each of them is going to be contributing to a different sum of ID, where ID is my get thread number. Aha, we did this before when we did this printout. We kind of showed what that was. Here I'm also printing out this piece of it and the ID number, same as before. All that's the same code as before. I am accumulating all to the various values of the sum, and at the end, I initialize pi, the return value, to be 0. I keep sequentially, not in parallel, contributing sum's contribution into pi, and then I print what pi is. How's my number? 3.142425. We did pretty well. I've parallelized this at least into 4 different ways, and hopefully this is pretty close to being 4 times as fast. It's not going to be perfect. There is some overhead. I still have to do this adding up everything of the sums in sequential order, but I'm getting close to a 4-time improvement in speed. Love this. Did pretty well. Let's increment this to now, just change one line to say, rather than num steps is 10, number of steps is now at 1,000,000. And how am I doing? 3.1415926535897. Not bad. Not bad. So we're actually doing fairly well. This is a pretty good job. I'm feeling very confident about this. I love this. Now, I gotta take a second back. How do I parallelize computing sum? You remember that sum at the end, I had to stop. And remember, look, that was fine when I did this. I'm stalling for 4 threads. It's not too bad. It's only 4 threads. This has nothing to do with its number of steps, number of threads. Could I parallelize that threads? What if I had a lot of threads? Could I parallelize the computing the sum in some way? That would be interesting. Well, let's try this one. Let's bring that pi, remember that pi plus equals sum of ID? Let's bring that into the loop somehow. So now I put this bracket around parallel OMP parallel, pragma OMP parallel. So here's this bracket around that. And I brought the pi computation into that loop. Let's try it. I'm so excited. Now, be a little bit more efficient. Just that last group of 4, let's bring that in there. What do I get? Okay, so the summation is now inside the parallel section. So there's not much speed up here, right? You only keep speeding up for these 4 guys. But what happens when I run this? 3.1415926535897 Uh-oh. 3.13? Wait. I've got number of steps is 1,000,000. Wait, I got 1,000,000. I got 1,000 threads here. Look, 1,000 threads. So I added more threads here, a lot more software threads. That's different. So I cranked that up. I still got my 1,000,000 steps. That's doing fine. Except, do I add 1,000,000? That's like 100,000 steps. That's 100,000 steps. It's still pretty good. But look at pi. What happened to pi? That's crazy. Something went wrong here. And what's even worse is the value changes between runs. If I were to run this 10 times like you saw before, the value's going to change between runs. What is the problem here? Well, the problem somehow, the only thing I did differently was I added more threads. That shouldn't be the problem. I changed the steps down by a factor of 10. That shouldn't be the problem. I brought the sum into the parallel part. Can you see why that's an issue? What's going on? This, my friends, is called a race condition. And this is a big idea. When you run in parallel, when you run with the parallel people, having race conditions is something you have to really work hard to avoid, because it's a way to have garbage values. It's a way to have not just garbage values. I mean, this pi calculation is almost useless anymore, right? I was trying to do this so I can get a nice, very, very high resolution value of pi. I'm not getting that at all. And it's going to change between runs. You can't have that. We can't have this. Is again pruning that non-determinism. And one of the things is this race condition is the reason for that. What if more than one thread grabs that? So more than one thread grabs, watch this, pi equals pi plus my sum of ID. So far, so good. That's no problem. So what's happening? And this is at the end, by the way, the loop, all that main loop. Here's the main loop for 100,000. Here's the main loop for 100,000. This is just a little bit here at the end where I have to now do this calculation at the end. This is problem, because what happens at the end of this is the day. This is the work day. This is the work day. And now I'm at the point where all 1,000 people have to contribute their computation into the value of pi. Okay? Plus equals. Plus equals says pi equals pi plus there, which means what happens if two parallel threads grab the old value of pi? They both grab the old, let's say the pi is 3. Let's just say pi is 3. So it's been added up, now it's 3. Okay, I'm going to add my little fraction to that. Maybe both of us calculated 0.05. So 0.05 should be 3.1 at the end of the day, right? If here's pi at 3, and I calculate 0.05, and you got 0.05, and we both calculate our piece to it, so pi should be 3 plus 0.05 plus 0.05 is 3.1, okay? And then there's more to get the 4, blah, 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 etc. So stay with me. We both read 3. You can see this race. Can you see it happening? I'm going to slow motion. We both take our 3. We both internally add our 0.05. And we both, now you write first. Now 3 becomes 3.05. And I write mine. Pi becomes now 3.05. We both wrote our 3.05. And it's not like one of them was thrown away. The first one was thrown away because this could have been 0.06. But there, and then 0.05, it wrote over that. Trouble. The only way to deal with this is we gotta figure out. So that's the problem. This is called a race condition. This is a non-deterministic. By the way, this is when they were both the same. What if one is bigger than smaller? What if this is 0.06 and 0.05? And here, whoever writes last is going to be able to own that number, and the other one is lost. So it's not deterministic, and I've lost values. So this is really trouble. We've got to figure out how to prune this. So we're going to look at how to kind of lock the other people out of code that really should be sequential. Now, we had a sequential at the end, but we want to be able to do this in a clever way that we still get a little bit of parallelism, but we got to have a lock. There's got to be a way to lock people out of this to be able to do this in a kind of clever way, okay? So let's see if we can do this. I still want to be able to imagine. I still have 1,000 threads. I still want to be able to parallelize my contribution to pi, but I want to do it in a way that makes sure that not two people aren't both trying to write to pi at the same time. Because if they're independent, if 1,000 people never happen to run it and override at the same time, I'd be fine. It'd be great, and it'd be parallel. Each one is contributing their pi rather than having one serial guy at the end. So I like that. I want to get to that place, but I need some help from software to support and prune that race condition, okay? We'll see you in the next video.